everyone. My name is Giovanni Luca Sferrazza, but everybody calls me Gianluca. And today I will talk about Non-Markovian dynamics of a qubit due to accelerated light in a lattice. And in the next half an hour, I will explain in detail what all this mean. But before doing so, just let me acknowledge the people with whom I collaborated. So first of all, the first author here, Marcelo, with whom I had the pleasure of collaborating, and also Daniele, and clearly Francesco, which is here, which is my supervisor. So, okay. Now this is a brief. So I'm sorry for those of you that attended my PhD exam, because I will repeat some stuff, but it will go slower. So you can also ask questions, and I will say something more also. So just to give you a brief overview of what we will see. So since not all of you are familiar with this waveguide QED research field, I will give you really a brief introduction to the results in waveguide QED that I think that are most important, and also some applications. After that, I will go deeper into the work, in particular by sketching some prerequisites that I think that are needed in order to fully appreciate the work. And then we finally will study the interplay between waveguide QED and this block oscillations phenomenon that I will tell you about. And so ending up in this strongly this non-Markovian dynamics, this is which is essentially caused by having block oscillation phenomenon in our lattice. Finally, I will also give you an outlook of this project here that I'm working on, which is essentially using non-Markovianity to probe topology. And so this outlook came out from useful discussions with Professor Marco Di Liberto, with whom I will hopefully have the pleasure to collaborate with next semester, next year. So let's start by the glimpse into the waveguide QED world, and just to set the terminology. So what I define as a traditional quantum optics is essentially the interaction between atoms and photonic environment, which are the conventional ones. So essentially the most conventional one will be free space, where you study the quantized electromagnetic field modes in free space. But then what people realized, like in the 60s, is that if you confine light, and I also am including that in traditional quantum optics, when you are trapping light inside the cavity, then you can reach new physical regime, which are kind of the opposite of what happens in free space. So in free space, what happens is that essentially the vacuum fluctuation of the quantized electromagnetic fields will drag if you start with an atom in the excited state, will drag the excitation to the ground state. And this is an inevitable process, and this is an irreversible process which ends up in spontaneous decay. But what happens if you essentially enclose your atom in a cavity? Then essentially the cavity is providing you some length scale which select a given wavelength, say. And if you tune, say, the atomic frequency resonance with the cavity frequency, then you engineer something which is really the opposite regime with respect to spontaneous decay, where you will have this fully reversible dynamics, which is called which are the celebrated vacuum Rabi oscillations. Now the idea is that so in the 80s, people really experimentally implemented the theoretical work, which was already almost really advanced already in the 60s, and they used many experimental platforms. But what I would like you to think about when we think on this application here is essentially circuit QED platform, where really you have this one-to-one map from the theoretical model to the experimental one, where the cavity here is replaced by this microwave resonator or LC circuit, and then the atom is essentially replaced by this transmon qubit, which is something like an LC resonator, where you essentially provide some nonlinearity in the potential in such a way that it behaves really like a two-level system. Now we will enter instead the field of waveguide QED, or light matter interaction in structural environments, where essentially now for a moment forget about the atom here, just imagine multiple copies of the cavity that we saw before, and now this cavity are also forming like a network of a couple cavities, where the coupling is provided by the fact that if you have an excitation leaving one cavity, say, there is a non-vanishing transition probability for the excitation to up to the neighboring cavities. Now, now, if you imagine to enforce translational symmetry on this network or couple cavities, then block theorem holds, and essentially you will end up with a spectrum which features energy bands and energy gaps, as you can see here. Now, imagine how to place the atom and coupling it in the same way that we saw before, for locally to a given cavity, say. And then imagine that everything is fixed, but you can tune at your will and shift the atomic frequency just for sake of simplicity. So essentially, you can imagine to tune the atomic frequency inside an energy band or in an energy gap. And this slide here is just summarizing what are the various physical situations. So maybe the first two columns are the trivial ones. The third column is the important one. So just briefly discuss the first two, which are the trivial ones. So essentially, if you tune the atomic frequency inside an energy band, then you will have a lot of traveling modes available for the atom to decay in. And indeed, this is essentially spontaneous emission, because if you depict here the photonic population as a function of time, so here you have the cavity index, the atom is placed in the middle of the chain, and you let time evolve in the y-axis. As you can see, essentially the photonic excitation will leave and move away from the atomic position, because there are many traveling modes available for the atom to decay in. And indeed, if you study here the atomic population, as you can see, the atom is undergoing a spontaneous decay and a spontaneous emission in an exponential fashion. So here, really, the only non-trivial stuff is that you can engineer some sense. If you change lattice, you can change the local density of states, which at the end is determining the decay rate. But other than that, is essentially spontaneous emission. Now, also this, if you couple an atom stronger to one cavity, it will see essentially only one mode, and then you will have something related to the previous vacuum Rabi oscillation that we saw. But then what happens if you slightly detune the atomic frequency from the energy band? Then if you plot here the photonic population as we did before, as you can see, there is like an orange line which is leaving with the atomic position and is not moving away. So this is like witnessing the fact that there is a photonic excitation which is trapped around the atom as time goes by. And if you plot the atomic population here, as you can see, the atom would like to decay, but then it undergoes damped oscillation, and in the long time limit, this value will stabilize to a given value, which is kind of comprised between 0 and 1. And the reason why is that if you start, say, with an initial state, which is the atom in the excited state, and you wait enough time, you will end up with a stationary state, which is this big psi here, which is an entangled atom photon bound state, which will be an eigenstates of the full Hamiltonian. Now, the way to see this kind of structure is essentially the fact that you have the atom here, which is coupled to this cavity, and there is a photonic cloud really trapped and localized around the atom, because in the energy gap, there are no really modes for the photonic excitation to really move away from the atomic position. Now, you can ask then, why should we care about this kind of structure? And the reason why is that I showed you before some Hamiltonians, and the atomic part was only involving 1 emitter, but I mean, nothing prevents you to consider more than 1 emitter. And then if you essentially consider this emitter coupled to your waveguide, and you trace out the degrees of freedom of the waveguide because you don't care, you will end up with a master equation whose third term here is taking into account dissipation and incoherence processes, But then you can show that whenever you detune the atomic frequency in the same way that we saw before outside the energy band, then this third term vanishes because it's essentially related to the local density of states, which is zero outside the band. So you will end up with a coherent interaction between emitters, as you can see, and you can use this waveguide QED-based platform for useful applications, such as, for example, trying to engineer a quantum gates between qubits, or, for example, if you couple many emitters, you can simulate maybe complex many-body phases, say, that, and so you can use that for quantum simulation purposes. So I don't have time really to only focus on another very cool aspect of the field, which is but I will briefly sketch the fact that if you have your photonic structure with an energy spectrum which features bands, then you can endow your band structure with a non-trivial topological invariant. So already people in condensed matter figure out that whenever you have a topological invariant which is non-vanishing, you have some sort of edge physics which is going on. But then also people realize that if you couple atom to a photonic analog of what is a topological insulator, then you will get some adding feature to your light matter interaction. In particular, you will add some feature to your atom photon bound states that we saw before. So just to summarize here, the state of the art, which clearly this list is not complete, but is simply the list of the topic that I dealt with and I worked on a bit. So there is topological band theory meeting waveguide QED, which is essentially related to the previous slide. Then non-Markovian regimes, whenever you couple your atom to your waveguide, so in this sense, you now, again, you are in the spontaneous emission regime, but you somehow put some obstacle, something which provides a feedback effect to your atomic excitation. And then you will end up with some non-trivial non-Markovian dynamics, because essentially you're providing a second time scale to compare with the natural time scale, which is the decay time of the atom. And last but not least, for example, try to engineer due to, say, the coupling or maybe the photonic structure of your environment, to try to engineer directional emission, like chiral emission, such that you can use that for state transfer protocols of quantum communication. So I try to put essentially boundaries between this stuff, these topics here, but really there is a non-trivial interplay going on between them. Just to mention one, if you, for example, read this night's paper from Daniele, he essentially managed to engineer this chiral emission by coupling your atom to a photonic analog of an integer quantum Hall droplet, which is really much related to topological band theory in this case. But moreover, since you are adding magnetic fields, there is also a non-trivial non-Markovian dynamics going on. So it's also related to the non-Markovian regime. So just to sketch the fact that there is a non-trivial interplay going on between these topics, but I will try to focus here on the non-Markovian regimes. And in the outlook, we will see some connection with topology again. So let's start. Yes.
For you to have all these topological effects,
Yep.
you need to have open boundary condition.
No, I mean, in this case here, in this case here, no, it's so that you want, for example, to engineer. In this case, he was able to show chiral emission in the bulk of the sample. But here is because essentially, you see, there is an electric field and a magnetic field which is providing you for this Hall effect, essentially for your when the atom releases its energy, will be forced to like move in a sort of waveguide, even if it is 2D. So now let's start with the prerequisites. So first of all, non-Markovianity, just a simple-minded definition of non-Markovianity. So just to set the context, so I think that everybody else is more expert than me on open quantum systems. So you have but I will sketch again the usual picture that you have. So you have a small system, a big environment which is surrounding your system, and you are studying essentially. You don't care about the environmental degrees of freedom, and you trace them out, and you are ending up with with the dynamics only involving the system degrees of freedom, where system is the thing that you care about. And in general, under some mild condition, you would end up with, in general, an integral differential equation, like that one, where K is a memory kernel, in the sense that K is taking care of the path correlation function, which essentially are providing some sort of informational backthrow to the system. That's why it's called memory kernel, and it will give you this integral differential equation. So whenever you are write something like that, you are dealing with non-Markovian dynamics. But what I mean by Markovian dynamics is then, if you're able to use some under some assumptions, say you are able to write this K as something proportional to a direct delta function, then as you can see, the integral will collapse to a single time. And then the equation of motion becomes time local. That's what I mean by Markovian regime. Now, if you translate everything into the waveguide QED terminology, this G here, I define this G as essentially the evolution operator written in the basis, in the position basis, okay? And this is the propagator. Now, the last two lines are simply like to say that essentially if you evaluate this propagator at the same position, then you can show that this G and the local density of states are related through a Fourier transform between each other. But then if you do some, use some sort of Wegener-Weisskopf type of argument, then you are able to write down an integral differential equation for the atomic population, which looks formally the same as the one that we saw before. But as you can see, the memory kernel K here is embodied by the green function here of the bath. So if you, for example, enforce weak coupling regime or omega inside the band, then you can write this G as something proportional to a Dirac delta. And hence, after this wave arrow, as you can see, you get a time local equation, so a Markovian dynamics, whose decay rate, as pronounced before, depends on the local density of states. The second prerequisite is how do you add electric field in your type binding Hamiltonian. So this is like the first and the simplest instance of type binding model, a uniform chain with uniform coupling strength, with uniform hopping rate. Then you can diagonalize very easily, like in a couple of lines, and you will get a very nice sign-shaped energy dispersion. And the eigenstates are essentially block waves, like plane waves in a discretized lattice. Now, how do you add an electric field? So here we are in one dimension because we are considered the easiest instance of a type binding model. So if you are in 1D and you are considered classical electrostatic, but you are have continuous space, how do you add a uniform electric field? You add a linearly increasing electric potential. So you do the same thing here, but simply taking into account the fact that your space is discretized, okay? So you add a linearly increasing on-site potential on the site of the lattice. Now, the cool thing is that you can evaluate the propagator, as we saw before, written in the basis of K states, which are the eigenstates when F is equal to 0. And you will, if you do some calculation, you end up with a delta Dirac, where the argument vanishes whenever K is satisfying Newton's second law, as you can see. If you take K dot here, you get K dot is equal to F, which is actually P dot equal to F for Newton. Now, this is the core idea behind block oscillation, essentially, at least in 1D. So the idea is K is not an eigenstate anymore, but still it is undergoing a simple evolution if you apply the evolution operator, since this K is mapped to K of T, where K of T is satisfying Newton's second law. Now, if you start with the K states here, like pi over 2, and you switch on the electric field, as you can see, this K will move in a linear fashion until it hits the Brillouin zone boundary. Then it will be, it's not depicted here, but it will be backscattered to the other time reversal invariant momenta, because I remind you that the Brillouin zone is actually a circle in this case. So pi and minus pi, which are the edges of the Brillouin zone, are actually the same point because they are connected by a reciprocal lattice vector. Now, this is sufficient for us to just to write some semi-classical theory. So essentially, whenever you have k, you substitute this static k with k of t, and that's it. So you have omega of t now, where you substitute here k with k of t, and the same thing for the group velocity. Instead of having k here, which is the derivative of this omega of k, you will get something which is time dependent through this k of t dependence here. Now you can integrate the group velocity and getting the essentially the kinematic law for the average position in real space when you consider a wave packet in your tight binding lattice. And as you can see, it will move back and forth in an harmonic fashion, whose amplitude is determined by this psi, which is the ratio between the hopping rate and the electric field strength. Now, these are bulk oscillation. Now, let's see what happens when finally we combine waveguide QD and block oscillation phenomena. So again, now this will be the setup for the rest of the talk. So the qubit is coupled to wave coupled cavity array in the zeroth cavity, and then you apply an electric field. Now, if F is equal to 0, okay.
So this means that if the electric field is very high, there is no movement around.
Yeah, it will. Yeah, F that is very big, it will create some sort of confinement. Indeed, like the electric field creates some sort of yeah, the oscillation will take place in a very small portion, like a sort of something which is very localized. Yes. So F has some power of localized stuff, as we will see.
Is there like a more physical way to see it? Because I don't know. I don't really have like a physical way to get a grasp of it. You have this linearly increasing electric field, right?
Yeah.
Why?
Okay, let's see.
Why the stronger it is?
So let's take the extreme case, F equal going to infinity, right? Essentially, the atom will only see so the energy scale do not count anymore, and essentially you will see only one cavity. So everything collapses to a single site. So that's why there is this confinement effect in an intuitive way.
He means that the cavities are like uncoupled.
Yeah.
Okay.
By the way, we will see that the electric field in general as
Yeah, that was completely.
yeah, because you are living in a band.
Yeah. Okay. That's hard to get a grasp on, but I get that.
So look at that. You start here, okay? And the derivative is positive, which is the velocity. Okay? You arrive here, which is the minimum, velocity is 0, right? Then it will move the k momenta here, and now it reversed the slope, which is the velocity. So it's coming back. That's why there is the oscillatory behavior. Okay, so this
Gianluca,
is
can I ask a question?
No, yes, I'm joking.
Okay. So, just a curiosity, actually.
Yeah.
So these block oscillation, right, are usually studied for tight binding lattice in which you have this characteristic cosine shaped dispersion law.
Yeah.
But my question is, like, if you instead have a linear waveguide, right? So you have a dispersion law which scales as the absolute values of k. Would you still have these oscillations? Because your argument of the change of slope.
No, I don't think so. I mean, if you have a real waveguide and you have this linear dispersion law, then really that works as if you are in free space, like in one dimension, right? Because you substitute k with k of t, and this is linearly growing, like to happen according to Newton law. So
okay,
I don't know. At least
but even in that case, you have at k equals 0, you have the minimum energy. So if you start going towards that minimum, then you change the slope, right?
Yeah. But then it will increasingly growing if you don't. If there is another maximum that forces the thing to go back, then it will.
Okay.
You see, you have only at least one inversion of motion if you choose the right direction of the electric field, and then that's it.
Okay.
I think.
Okay. So you have only a single, if you want, you have only a single oscillation. So it goes in one direction, it goes back, and then stop.
Yes.
Okay. Okay. Thank you.
Yes. You're welcome. So if f is equal to 0, like I'm repeating myself many times, and omega naught is placed inside the energy band, then you will get spontaneous emission. But the cool thing is that the energy spectrum of the Hamiltonian drastically change whenever you add an electric field. So you go from an energy band to a yet simple energy spectrum, which features, by the way, a ladder of equispaced energy level, whose spacing is given by the electric field strength. And this is the very celebrated Wannier-Stark ladder, okay? Now you can also work out explicitly the eigenstate, and this is done in this very nice paper analytically. And the eigenstate written in position space are essentially linear superposition of ket position basis whose amplitude is given by this J. What is this J? This J is the Bessel function of the first kind. Now, how this function behaves? So first of all, notice that here there is the N clearly, which is labeling both the eigenstates and the energy eigenvalues. But N is the same label that we are using, for example, for the lattice index. And this is not done by chance, because essentially phi N, you can show that phi N is localized around the nth lattice site. As you can see, for example, here, this blue Bessel function is for n equal 10. So essentially there is a one-to-up map between the eigenenergy. So the farther you go in energy, say from 0, the farther you are moving the eigenstates, which is localized farther and farther in your lattice. Or, okay, the other stuff to take care about is this argument psi. Now psi determines in some sense the range of the Bessel function. As you can see here, we can take the limiting cases. If psi goes to 0, everything collapses to a single orbital, which is somehow related to the question that you asked. And when psi goes to infinity instead, as you can already see here from this oscillatory behavior around the center, this can be essentially approximated by a sign-shaped function, okay? So these are the two limiting cases. Now let's see what happens now when you want to study dynamics. Okay, like intuitively, you are adding another energy scale, which is the electric field strength. And if you go in deeper into details, you have two energy scales to compare. First, you have the average coupling strength to your photonic system, which is given by this G bar, which is G over square root of psi. Psi is the one that we saw before, versus the electric field strength. Now, if you take the ratio and do some algebra, you're essentially comparing two competing time scales. So TB here is the block oscillation, that is the time taken for a block wave to swipe out the whole Brillouin zone, and gamma, which is the Markovian decay rate. So let's study the two opposite regimes. So strong force regime means that gamma TB is much smaller than 1. And in this case, we set the parameter in such a way to have 10 to the minus 3. And then, so this is always the same setup. So what happens? So if you see this black box, just to understand very intuitively what will happen, if you imagine that F is very big and G is very small, the atom will almost see only one photonic mode. So we can already intuitively think about vacuum Raspberry oscillation. And indeed, this is what is happening. Indeed, if you see the atomic population here, all the cases that we are considering are undergoing these Rabi oscillations. So let's see what is, for example, the solid blue line in terms of photonic population is this plot here. This plot here is essentially for omega naught equal to 0. As you can see, you are periodically populating a bunch of cavities around the atomic position, which take the shape of the zeroth Bessel function as expected, right? But now the cool thing is that if you detune the atomic frequency from 0, for the reason that I told you before, you are coupling two modes which are also shifted in position space. So essentially here, for example, for omega equal minus 3f or omega not equal 3f, you are coupling two modes which are detuned in position space with respect to the atomic position. And so that's why we call that regime chiral vacuum Rabi oscillation. So let's now analyze the other opposite regime, now weak force. So weak force means that gamma TB now is much greater than 1, okay? So this is what happened from numerical simulation in various regimes. So it's a bit of a mess. So just focus on two paradigmatic cases and leave the other cases for questions, okay? So let's study this. Again, as I said, I will repeat myself many times. For f equal to 0, this is kind of also I am in real life. So f equal to 0, you will undergo spontaneous decay. If you do the photonic population real space, the two-wave packet will move away, and that's it. But if you do a Fourier transform of this plot, as you can see, you are constantly coupling to the same modes, which are these two guys here. So at t equal to 0, omega naught is equal to 0, you are coupling to these two modes. If f equal to 0, this will be the case for all the times. Now, if you switch on the electric field then, and you study the Qubit population, as you can see, now there is a non-Markovian dynamics, which is witnessed by the fact that you have these peaks, these revivals here. And the way to understand these revivals is actually see what is happening in terms of the photonic population in real space. As time goes by, now everything seems more compact simply because we changed time scale from j to the minus 1 to time written in block oscillation period unit. So as you can see, the atom for the first instance of time will essentially release two-wave packets, but then both of them will undergo an inversion of motion and they will come back to the atomic position. And the reason why that is that both of them are undergoing block oscillations. And indeed, this is the picture, which is the right picture, because if you take the Fourier transform, as you can see now, what before were fixed momenta, now they are essentially linearly, essentially evolving according to a linear fashion, as you can see, which is what is provided by block oscillations. Now, if you see the other, so we described this B1 case, but if you see just to see how they look like the other cases in terms of revival spectrum, these are the features that reminded us of some paper dated back to Miloni in the 80s, where he was studying here in the right paper, essentially an atom coupled uniformly to a ladder spectrum as the one that we have, but he considered the same coupling strength in this paper here with collaborator to the same same coupling strength to each energy level. So in a sense, our model is more general because we have a sign-shaped coupling mode function. But anyway, we can retrieve this case as a special case. If you are interested, I can also discuss that for question. But in the left here, then after some years, he studied, so this is like a theoretical paper. Then he analyzed something which is also more pragmatic, where he was studying atom emitting in a multimode cavity. That if you enforce weak coupling regime, then the atom is seeing like a ladder of energy levels like this one. And as you can see, then the revival spectrum is very similar to the one that we have. So that pushed us to really see some analytics. So as I said before, you need only the memory kernel to write down this integral differential equation. And we already have the eigenstates. So we have the memory kernel. If you don't see from this infinite series that this is not a Dirac delta, then you can essentially resum this thing by using a Bessel function properties. As you can see, you would end up with something which only take into account the zeroth order Bessel function. So as you can see, this is very different from a Dirac delta. So this is a non-Markovian dynamics indeed. So if you so this is the integral differential equation that we saw before. Now we apply the fact that we are in the weak field limit, so we can approximate each Bessel function, which their sign-shaped asymptotic limit, and do some math, and you end up with a differential equation which mathematician cast them in what is known as a delay differential equation. And as you can see, there is a very strong formal resemblance in mathematical terms with the question that Miloni obtained in his paper about the Fabry-Perot resonator. But here there is a non-trivial difference. So here the feedback mechanism is provided by the fact that it is placing essentially boundaries which essentially provide the feedback mechanism, because the photon will bounce back due to the mirrors back to the atom. Now here, and here again is connected to your question, here we do not have any physical boundaries, but the feedback mechanism is provided by adding the electric field. So in a sense, in an intuitive way, what is happening is that the electric field, when you switch on the electric field, now K is no more a good quantum number. It will evolve a photon or excitation, know that they are living in a finite region of momentum in an finite energy window, which will provide some, also if you do some math, length scale, which is some sort of localization. So in a sense here, the flight time for the photon to bounce back and forth from the mirrors is replaced by the Bloch oscillation period, and the distance between the boundaries, the mirrors, is replaced by the Bloch oscillation amplitude in a sense. So just to briefly discuss an outlook, because maybe we are running out of time, which is interesting. So just a brief review, just now forget about everything we said, and just a brief review of the adiabatic theorem. What the adiabatic theorem says is that if you have an Hamiltonian which is time dependent, whose dependence is very slow, in the sense that you have a time dependent Hamiltonian because you are switching on some parameter, time dependent parameter, which is evolving very slowly compared to the time scale dictated by the energy gap of your system, then what the adiabatic theorem says is that if you start at time 0 with n0, which is an eigenstate of your Hamiltonian, then at time t, you will be adiabatically connected to the anti-eigenstates of the Hamiltonian evaluated at time t, with an additional phase factor Cn, which is given by the product of two phase factors. One phase factor is the dynamical phase, which is essentially is the natural generalization of the phase factor that you would acquire for an eigenstates with a time-independent Hamiltonian. And the second, which is the most important one, is the geometric phase, which is this guy here, which is called geometric phase because you can do chain rule and write that in terms of an integral over a path in phase space. So it doesn't depend really on time. So I'm just leaving here time, but you can write it in terms of the path that you traveled in phase space, where phase space, I mean these parameters that are changing, slowly changing in time in your Hamiltonian. Now, the problem is that in our case, so the 1D chain with the electric field, in our case is the one that provides the time dependence. So here will be K of t in our case. But anyway, this geometric phase is 0 in our case, okay? So we only have the dynamical phase. So by the way, if you integrate the dynamical phase from the wave packet when you have the atomic frequency tuned to 0, and you essentially integrate from Ti to here Tb over 2, you can show that this is equal to 2 psi, okay? But 2 psi is the thing that is appearing in front of the half period revivals. Okay, so essentially the half-period revivals can be seen as an interference effect between the dynamical phases. So this is the thing that we thought about and then asked, what happened then? So there is a signature of the interference effect due to the dynamical phase in your equation of motion. So we think about it and we said, okay, what happened if you generalize your tight binding lattice to something a bit more complicated, which is, say, the SSH model, which is very studied tight binding model with hopping and alternating hopping strength J1 and J2, because this is the simplest model that shows topology. So what I mean by topology, okay, is that you can compute essentially an index for each band, which is given by this expression here. So it's an integral over the Brillouin zone of this thing here, where your k are your eigenstate in k space. So the idea is this one: whenever J1 is less than J2, you have a gamma which is different from 0, which is pi modulo 2 pi. Or if J1 is greater than J2, you have that this is 0. Okay. So imagine now to put the electric field in your SSH model. The guess is that maybe there will be, if you study the non-Markovian dynamics of the atom, that there will be some interference effect now that are involving also the geometric phase. And I point out to you the fact that if you integrate from 0 to TB, really, you are actually evaluating, if n is equal to k here, you are evaluating the Zach phase. So the idea is to try to see whether there are some hallmark in the dynamical feature of your qubit coupled to the bulk of your sample, which depends. So if you see the revival spectrum of your qubit, maybe there are some revival features that are only dependent whether you are in the topological phase and maybe are missing in the topological trivial phase. So this is the end of my talk, and I thank you very much for your attention, and I'm open to answer all your question if there are any.
So just a curiosity
Yeah.
about the outlook you put. The electric field then recreates the chiral symmetry in the thing you are doing.
No, it somehow break it, right? Because here you are. So this is a good point. I mean, I thought about it. So if you add an electric field, you're adding it through on-site potentials. And on-site potentials are breaking chiral symmetry because you are connecting with the same chiral subsector. But
so how come you have non-zero topological states?
Wait, there is another symmetry which is quantizing your Zach phase, which is inversion. So essentially here, you are considering, moreover, you are in the weak field approximation. So somehow it's similar to when you study topology in 2D, right? And you are considering a magnetic field, right? And this provides you, if you change gauge, something which is time dependent, but very slowly. But anyway, you have topology. So in a sense, that's why I'm adding here the electric potential with the same strength on each unit cell, because this will prevent at least inversion symmetry in a cell.
Okay.
But anyway, I have to do the calculation, so, and also the simulations.
One thing about the simpler model. So you put the electric field about the question, the alpha. This one. No, the next one. Next one again. Okay. So here you say, if I understand correctly, that the kernel is not just a delta, but it's more of a delta, and that one, which is the non-Markovian effect, is caused by the electric field. But what if the electric field, which already has problems because of this discretization field, which are just now trying to understand, what if the electric field changes in time? What happens? What do you think should happen? Maybe go to a linear round.
Oh, this is a good question. I mean, if it changes in time, So you have a lot of time dependence now because you have something now which is f of t also in your equation of motion. Really, I don't know. I mean, it's something more complicated, but I don't know. I mean, this is a good question, but I don't know how to answer. I mean, you will have some. So.
The equation of motion for K should remain the same.
Yeah, should be the same. So essentially, what happens is that you have a more complicated eventually x of t, right? Because you have a v of t, which now is involving an f of t inside the thing. So when you integrate, you will have something more complicated in terms of these oscillations.
Maybe this, I don't know, might insert some geometrical phase.
No. If you have a 1D lattice,
It's not possible.
no, it's not possible because essentially this is the intuitive way that I can tell you. So first, if you do the calculation, you see that it's 0. But essentially, in a 1D lattice, okay. So I won't have time to go into the detail of topology, but essentially here you see you have a 1D chain. So the gamma here is related to polarization. So any invariant, topological invariant, is associated to an observable. In 1D is polarization. Okay. So how the Van center is moved with respect to your cell. Okay. Here, if you take a cell, it's just a single site. Okay. You cannot think in any way for symmetry reason to displace your Van center because essentially it will be centered around the lattice side, so you will always end up with zero polarization, which means zero Zach phase. So here you won't you can try hard as you want, but you don't induce topology because this one is topologically true.
The change of the function in the site doesn't matter because the sector are all.
I think if you no, because you maybe have to create some sort of spatial modulation in a sense that you increase your unit cell and then you can do topology. Because if you have at least 2 sites in your unit cell, then you can do topology. So some sense you have also to modulate in space other than time, so that you have to enlarge in some sense your unit cell, and then you can think about topology. Are there other questions?
Currently not. Thank you.
Thank you.
Thank you.
I stopped the screen sharing.